All right, so let's say given the situation here where we have a mass moving at a velocity of 5 meters per second, then at a later time it's moving at a velocity of 6 meters per second. And the question wants you to find the total work done for the object's motion between these two velocities. So to answer this question, we need to know the work energy theorem, which what this theorem does is it relates the work on an object to the change in the object's speed. And we can derive it by first applying Newton's second law to the question. If we define this point here as x1 and this point here as x2, delta x is going to be the displacement between them. If we apply Newton's second law and define the displacement vector as so, as the particle moves from x1 to x2, its speed changes from v1 equals 5 meters per second to v2 equals 6 meters per second. So we can use the constant acceleration equation to find the acceleration. Use this equation here, isolate for ax. We could bring v1 to the other side and then multiply it by 1/2 delta x. This is the acceleration for the situation. Plug this back into our Newton's second law equation, get this expression here, and then we can multiply both sides by delta x, and notice what happens here. The left hand side is equal to work, and we can do this trick on the right hand side by dividing both velocities by 2 and multiplying both terms by mass. These terms are actually equal to the kinetic energy at the 2 points. The kinetic energy can be defined as 1/2 mv squared. If we use this concept here, the left term is going to be equal to k2 and the right term is going to be equal to k1, so we can plug that in. K2 minus k1 is just equal to delta k, so we can replace that. This final answer here is the work energy theorem equation, which relates the work applied to an object to the change in its kinetic energy. We can apply this equation to the situation. Start with our work equals delta k and then write it in this form where the kinetic energy is equal to 1/2 mv squared. We can plug in our known values. We actually made an error plugging in the velocity values. v1 is supposed to be 6 meters per second and v2 is 5 meters per second. Sorry about that, guys. But the process is the same. So we can start evaluating this expression by first squaring the velocity terms, remembering to square both the amplitudes and the units. And then we can just continue evaluating by computing the amplitudes and the units of both terms and do a simple subtraction, and we get this answer here. So this is the net work being applied to the object between x1 and x2 if the scenario is actually opposite. The velocity of the object was slowing down from 6 meters per second to 5 meters per second. So this makes sense since the velocity is decreasing in our new scenario here. The work being applied onto it is negative. It's losing energy from the position x1 and x2. That's why we see its velocity decreasing. And if we didn't make this error, we would see that the opposite is true, that the work would end up being positive, and that would make sense because the velocity is increasing in the object. So that means that we're applying work to the object and the kinetic energy is increasing in the system, which results in an increase in velocity.